Okay, thank you. So I'm Miguel. I'm working in the Basque Center of Applied Mathematics in Bilbao, in Spain. And this result is an early result of a collaboration with Artemy Kolchinsky, University of Tokyo, now moving to Barcelona. And so this work is a bit related with what David presented this morning. We are interested in ideas from this field, stochastic thermodynamics, trying to connect ideas in thermodynamics, information theory. We are specifically interested in this quantity that David presented, the entropy production, which tells us about non-equilibrium behavior in systems. So we can so this is a result of the second law of thermodynamics that tells us that systems in isolation cannot decrease. And so classical examples, we can have two containers with different gases at different temperatures. And these define specific directions in which the system will behave until in which entropy will be produced. So entropy of the system will increase until the two temperatures are the same. And this is explained by the difference of kinetic energy, which is transferred from the hotter to the colder part of the system. So, and this is a very general relation which can be described in thermodynamics, and we can also think of it as describing the behavior of stochastic systems. For example, I can have a box of dice, look at it, I can shake the box, look again, and you can intuitively think what's the image before and the image after. So with this idea that disorder or uncertainty about our system, it can only become more likely if the system is isolated or only under the effect of stochastic fluctuations. However, this only applies for systems that are in isolation, and in life, biological or artificial, we're interested in systems that interact with an environment. And precisely when a system is not isolated, this second law of thermodynamics doesn't apply in this way, in the sense that non-out of equilibrium systems can resist these tendencies towards increasing entropy and maintain organized structures by continuously dissipating entropy to the environment. So in all of these examples where the system reaches equilibrium, this arrow of time disappears and the system stays there. But living systems are able to maintain this arrow of time by this continuously producing entropy, which counteracts the entropic tendencies prescribed by the second law. And so we can also think of about this as living systems or out of equilibrium systems being able to gather free energy from the environment to continuously sustain these organized structures. And as we saw this morning, the entropy production or the entropy production rate can calculate this free energy dissipation or this dissipation of entropy into the environment, which is what quantifies how systems are resisting these entropic tendencies. And during the last 20 years or a bit more, we have been developing this field of stochastic thermodynamics, which is enormously fascinating as it can quantify how this process happens in mesoscopic system. And we have things like Jarzynski relations, which generalizes the second law from this inequality that you see above. Entropy can only increase into an equality by adding these exponential relations. Or we have Crookes fluctuation theorem that tells us that the entropy, the production of entropy, or the entropy or the free energy or entropy that is dissipated when a system is interacting with an external environment, corresponds to the ratio, the log of the ratio of trajectories, the probability of trajectories of the system going forward in time versus trajectories of the system going backward in time. And this is directly related with this idea that out of equilibrium systems generate this arrow of time that creates an asymmetry between what trajectories look like in the forward direction and what a reverse movie will look like. And this ratio here is exactly the Kullback-Leibler divergence between probabilities forward and probabilities backward. So we have a connections between these ideas in thermodynamics and ideas in information theory. So somehow we could think of this quantity as how many bits we need to identify how surprising is a sequence going backwards. And this idea of the arrow of time has raised the imagination also even in popular culture. And recently we have a very bad Christopher Nolan movie about it. in which, so the plot is quite boring for me, but the interesting thing about the movie is that we have characters traveling forwards in time and characters that are able to reverse the arrow of time. And for these characters, everything becomes very surprising, like cars are driving backwards and things like that. So quantifying how surprising the world is for these characters traveling backwards is the same as quantifying this entropy production. So quantifying this Kullback-Leibler divergence that we see here. Okay, so partly of the question that we were interested in is how entropy production looks in large self-organized systems, or what kind of things we can expect. And this is so, for example, we know that the brain is an example of an emergent out of equilibrium system in which is continuously dissipating a lot of energy to maintain this network of signaling activity. And recently, some neuroscientists have become interested in trying to estimate or approximate entropy production in the brain. They have to do it at a very macroscopic scale, so it loses most of its thermodynamic meaning, although it is still a lower bound of the true dissipation. And they saw that the level of asymmetry in the brain depends on what you are doing. So there's some tasks like rest or tasks that are not very interactive, where your brain looks almost reversible, and tasks in which this level of irreversibility increases. Although you see, and there's also interest in connecting this irreversibility with ideas with consciousness, and you can see that comparing wakefulness and sleep, or wakefulness and different anesthetics, you can see decreases in this level of irreversibility. However, the levels of entropy that you see here are really tiny in comparison with the true thermodynamic dissipation that you will expect in a brain. So in a sense, looking at this coarse-graining activity is not very interesting is very completely detached from the entropy dissipation happening at the microscopic scale, and only captures a really tiny fraction of it. And so we are interested in trying to think of, so how can we better capture this emergent properties, the connection between emergence or the self-organization of structure, activity, and entropy production. So in very recent research with colleagues at the University of Tokyo, Hideaki Tsumasaki and Masanori Igarashi here in Hokkaido University, we came up with an analytical solution of the entropy production of very large neural networks in the form of a asymmetric spin glass-like model. And we saw that there was, disordered networks like this have different forms to have large entropy production, from critical points to quasi-deterministic chaos. So somehow, our motivation in this, what I'm presenting today, is how can we describe the part of the entropy dissipation that depends on the activity of large networks or interaction effects in networks. And there is a few proposals in this sense. There is one proposed by Chris Lin and collaborators in 2022. There is also work by Suzuki Ito. The first one tries to distinguish between entropy production in marginal distributions versus the true entropy production. And Suzuki Ito tried to decompose the entropy production of a system with two parts into the individual components and some other one emergent or synergistic part of the entropy production. Although these approaches in general either require special dynamics to work, or they do not have a simple operational meaning, in the sense that there is different ways to perform this part, this entropy production of marginals, and it's not easy to connect what these emergent effects are, or these interaction effects are, with different interactions in the system. So for addressing this issue, we started from a very general model with discrete states and continuous time, described by a rate equation, a master equation, in which you have the probability of a system and the rate of different jumps in the system. And since I described how we can define this entropy production rate as a Kullback-Leibler divergence, we can use ideas from information geometry to study what's the structure of the entropy production rate. So I'm going to describe very briefly, if you are not familiar with information geometry, it's a way to describe probability distributions as if they were points in a geometric space, and use ideas of geometry to understand the relation between different probability distributions. So for example, we can take the idea of a projection in Euclidean geometry in which we project a point P onto a subset Q, which here is this line, and trying to find which is the closest point to P in Q. So when we don't have a Euclidean space, but we have some manifolds described by probability distributions and Kullback-Leibler divergences, we can generalize this idea by defining different types of geodesics, like specifically dual pair of geodesics, combining linear mixtures and exponential combinations. And this allows to decompose a Kullback-Leibler divergence between 2 points P and Q into 2 parts, one from point P to the closest point in a manifold Q star, and the distance between Q star and Q. Okay, this sounds very abstract, but this is used, for example, to think of a probability distribution in this point here, and think of manifolds containing, for example, interactions only up to some order. For example, interactions up to order 2 or 3 or more. And calculating these projections, we can decompose what are the different layers of interactions in a system. Hopefully this is going to become a bit clear later. So as we saw, the Kullback-Leibler, so the entropy production quantifies the divergence between the trajectory going forward and trajectories going backward. So with this idea, we can create manifolds of probability distributions in which we take the backward transition rates and we tilt them, we modify them by an exponential function, which gives us the type of geodesics that we need for this decomposition. Okay? And with this idea, so we define the entropy production rate as the distance between the actual fluxes in the system and the fluxes going backwards in time. And we can define a manifold of modified backward distributions and decompose this. So decompose this entropy production rate into 2 terms. This manifold is only going to contain lower order interactions. We're going to see later one example in which these interactions are of order 2, so only pairwise interactions. And so somehow this is trying to reconstruct the forward distribution by modifying the backward distribution with only interactions up to order n. So the closer we can get is going to be captured by this distance, and the remaining distance is going to capture the effect of higher order interactions in the system. So somehow this distance here is going to be the entropy dissipation or the entropy production rate that can be explained with simple interactions in the system, and the rest is going to be the entropy production rate that needs to be explained with higher order interaction effects. All right. So we explore this with a very simple model, a spin model with 2 groups of 100 spin and this transition matrix, which allows us to generate very easily oscillation in a network. This is like a inhibitory excitatory neural network, and we can find that there is Andronov-Hopf bifurcation in which limit cycles emerge when this parameter beta, this inverse temperature, is large enough. So we take this transition rate and we modify the backward rate by an exponential function that only contains pairwise interaction, as the forward model does. So we want to capture the entropy production that cannot be captured with pairwise interaction terms, and thus depends on higher order interactions in the system. And what we see is that so this is our first preliminary example. If we calculate the entropy production rate, the true entropy dissipation is this black line. So as we increase this value beta, the system starts to oscillate, the entropy dissipation rate increases and sort of stays there. But if we calculate only the part corresponding to higher order interactions, the behavior is a bit different. So it's very close to zero until the critical transition where oscillators emerge. And after that, it peaks where oscillations are large, but quite stochastic. So when these oscillations become very deterministic, so here on the left, the system is very deterministic, and on the right is, on the left, the system is very stochastic, and on the right is very deterministic. So we see that when oscillations become very deterministic, these higher order effects decrease, suggesting that this measure is able to capture more emergent effects that take place around this critical phase transition. Oops. So to finish, we have suggested this decomposition of the entropy production rate that could allow us to distinguish between dissipation that corresponds only to individual components or simple interaction between components, and this other part, this higher order interaction part that depends on collective effects in our network. And so this is a very abstract and mathematical result, but we are interested in how this can explain properties of biological systems, living systems, or intelligent agents, with the idea that such systems must be able to maintain these organized structures dissipating entropy that must contain these higher order interactions. And it will be interesting to study how we can generate systems or models or observed in nature having large dissipation at this macroscopic interactive level. And also some positions in this topic, Predocamposto, will be available in the next available year. So if you're interested in these topics, please get in touch. And thanks a lot.